ladies and gentlemen, welcome back to another round. Hopefully you have watched the Equilibrium Refresher lecture, or you understand equilibrium before we get into this, because we're going to apply some of that stuff. If Mr. Doolin just happened to mess up and put these in the wrong order, please go back and watch the Equilibrium Refresher before you start this so that we can understand and be on the same page. Okay, so I've got a statement written on here. Galvanic cells have a positive E cell value, and they are thermodynamically favored. We understand when we write these redox reactions, these galvanic cell reactions, that they're going to travel in the forward direction. And so hopefully at that point you understand the forward reaction is favored, which means I'm not at equilibrium. So if I use again my generic A goes to D, right? We understand we are not at equilibrium. We understand that I'm going to just put FWD, forward reaction is favored, right, at standard conditions. And remember, standard conditions are your 25 degrees Celsius and your 1 molar concentrations, okay? So forward reactions are favored at standard conditions, and they have that positive E value, right? They have that positive E cell value. And so if we use and apply equilibrium to this, what that's going to mean is that my D squared over the concentration of A, if I use Q here, that my Q is greater than my K, right? And what that means is that my reactants are going to be consumed, my products are going to be produced. Now there is this really quirky thing that happens with batteries, is that they die. They actually run out of energy at some point in time. They don't produce any more electrical current. And so what we need to understand about that is the battery's not dead. The reactions are still going on. But what happens now is that Q is equal to K. We are at equilibrium. When batteries die, they're not dead. The reaction hasn't stopped. It's just that they are at equilibrium. And so you do need to notate that there, that when batteries die, it's because they're at equilibrium. And let's go ahead and draw a real quick, just small, quick and dirty, and this is going to be one of the ugliest galvanic cells I've ever drawn, and you're welcome for that. All right, and so that's just basically it. And so at equilibrium, well, I guess let's start. When we start the reaction out, well, guess what? I've got a net electron flow if my electrons are going in that direction. And that forward reaction is favored. But what happens when I start approaching equilibrium? Well, I get electrons transferred back in the opposite direction. Because remember, equilibrium means the rate of the forward and the rate of the reverse is equal. And so if I'm getting the same number of electrons transferred in both directions, it just means there's no net electron transfer. Right? There's no net electron flow, if you will. And so I don't have any voltage. The voltage is dead. I don't have any potential difference. The battery is dead. Okay? Okay, and so hopefully you got that and you kind of understand and can wrap your head around it. So now let's take a look specifically at this Nernst equation. All right, and so Nernst equation is actually simplified. I'm going to give you the simplified version, is that my E cell value, this E here, represents when I'm at non-standard conditions, is equal to my E cell value at standard conditions minus some constant number, which is 0.0592, over the number of moles of electrons transferred times the log of Q. And so again, remember, Q is equal to that concentration of products over that concentration of reactants with my exponents. I'm going to put M and N up there rather than zeros. So my Q value, again, I'm discussing equilibrium here, so it's that log of products over reactants. And so you have to understand, I'm going to draw our original reaction here where we had zinc plus copper 2 plus, and that gave me copper plus zinc 2 plus, right? And remember, this was at 25 degrees Celsius, and it was 1 molar solutions. And so you have to understand too, when you apply these molarities, that means that this is a 1 molar solution and that this is a 1 molar solution. Those are my half cell containers, right? And remember, when we write these equilibrium expressions, we leave solids out. So those two aren't going to be included into our equilibrium expression. So the question becomes, what happens if I actually have 2 molar copper plus? So what happens if I have 2 molar Cu2 plus solution? how would my E value, how would my voltage, my potential difference, how would it be affected? So I'd say, how would E be affected? And notice the difference here. I don't have that not symbol up here. It's just E now, because now that I'm at 2 molar, I'm not at standard conditions. This little E naught value here means standard conditions, all right? So if we take a look at our Q, right, in this particular case, Q would be equal to the concentration of zinc, 2 plus, over the concentration of Cu, 2 plus. Don't forget your ion concentrations there, right? Because zinc's a product, copper's a reactant in this particular case. And so at that point, my Q value is equal to 1 over 2, which is equal to 0.5. Now, this is where we need to have some number sense, all right? And let's go back and remind ourselves what we know about log. Log of 0 equals, log of 1. The log of 1 equals 0. The log of some number less than 1 is equal to a negative number. The log of some number greater than 1 is equal to a positive number. And if you don't believe me, just pick up a calculator and hit log of 0.5. It's going to give you a negative answer. And then hit log of 2 and it's going to give you a positive answer. All right? And so when we look at this, when we go back, this value plugged in right there would actually give me a negative number. And so now, and I know I'm going to be writing on the bottom of this page, it would be E minus, or E, my non-standard E value would equal to my E value at standard conditions, and I would just use standard reduction potentials to calculate this value, minus a negative number. Right? Because if this gives me a negative log, like log Q becomes negative times these numbers gives me a negative number, right? So this whole value right here would end up, in this particular case, being negative. Well, I can't subtract a negative. I can add a positive, though. So, right, remember, minus a negative becomes plus a positive. And so at that point, I would say, therefore, E will be larger. And I'd say than E naught, right? Because I'm going to end up adding this to the E naught value, which means my E value would get bigger, right? The forward reaction will be even more favored, and it will drive that potential difference up, all right? Okay, so hopefully you got that. I know that was really quick, really dirty. We're going to take a look at these examples in class, but if you got some questions, make sure you got them down. We will get them addressed. You can come to tutorials and get those answered as well. But other than that, I will see you in class.